Like Professor Guido Montpar from UCLA, his first lecture. Guido, please.
Yeah, good afternoon. Thank you, Shire, again. So then let's get started. We have a couple of days coming up. I have also prepared a couple of exercises that I hope to be able to distribute either later today or in the afternoon or something, and maybe a couple more tomorrow. And with the hope that maybe some of you will find together and try to take a look at some of those, and maybe as an excuse to meet somebody and think about some mathematics. Not that you were not doing that, but if you need an extra excuse, then that. All right, so for today, I want to discuss the problem of learning and learning from data, and what we actually mean by that, and how we have tried to conceptualize that and try to put that on a rigorous statistical foundation, and how we have worked from there to try to connect to machine learning topics and from a classical perspective, which remains relevant and contemporary for reasons that hopefully can become apparent in the course of the week. So this is the schedule, the learning problem, formal definition for learning, and then I want to discuss some complexity measures and some of the results that are out there on quantifying these complexity measures. Okay, so at this point, maybe it's a moment where I kind of try and should do a poll of sorts. I have talked with a couple of you. I know there are very diverse participants, some specialists, maybe some others a little bit less specialists. Yeah, so maybe you can give me a show of hands for the following questions. So the first question is, if I have read 150 pages of the book of Anthony and Bartlett or more. Okay. Question number 2. I have published a paper at iClear, ICML, NeurIPS. Okay. Question number 3. I have served as a referee for iClear, ICML, NeurIPS. Okay. Okay, so that's my poll questionnaire. Thank you for participating. All right, so the learning problem. So I found this cartoon. Actually, I did this drawing, but the story is, I think, quite appealing. I like it. So this is a little boy that is pointing at some object, and maybe you are asking a little boy if there is a tree in a picture, and you will most likely get a correct answer. And you may ask then maybe a 30-year-old or adult what the definition of a tree is, and you will most likely get an inconclusive answer. And this is something that I was debating with a mentor that I had as a teenager. He would tell me, what is a table? And back then I was like, what are you talking about? So because you start saying, okay, it has 4 legs, or it has a flat surface, or it's rectangular. And then he would tell me, there is always a counterexample. You can look at a table in the airplane, and so it will not satisfy your definition, or maybe somebody else comes up with a table that is round and it does not satisfy the definition, and so that somehow points at some interesting difficulty, which is that of things being somehow intuitively clear or being clear on the basis of examples, but not necessarily on the basis of mathematical description, on the basis of a formal definition. That's quite intriguing. And at the time, I think maybe nobody was thinking about this notion of learning from data, but this was a mathematics professor who worked on topology and asked me this question: what do we find a table? And I was intrigued by that for sure. Yeah, obviously this is one of the topics that nowadays you would say learning from data, so learning from examples. Okay, problem set up. Let's say that we consider the problem of predicting how a movie viewer would rate movies. And here there are criteria that the viewers use that are quite complex. And to model this explicitly is not easy. And therefore, it may be difficult to obtain an analytic solution to explain how viewers will rate movies. However, there is a hope that maybe data would reveal a lot about how people rate movies, and we might be able to obtain a sort of empirical solution to this problem that would say, how do we expect or can we predict how somebody is going to be rating a movie, even if we don't have a particular model or a particular function that is telling us that a priori. So somehow we're hoping that by processing some data, this data is going to speak to us about this question. All right, so here to try to do that more quantitatively, we might go ahead and describe a movie by a vector of features. And these features could capture things like the amount of action, or the amount of comedy, or the presence of a particular actor, etc. in a particular movie. So for each movie, we have a vector, components. Each component is a number that tells us how much of each of these particular items is contained in the movie. And then we could go ahead and try to describe a viewer in terms of corresponding factors, meaning how much does this particular viewer like action, comedy, or a particular actor, etc. And once we do that, we could imagine that if these two vectors align well, then this viewer probably will like that movie because it contains a lot of things that they like. And if they don't align well, maybe this viewer will not like that movie. So that's maybe an idea. So we could try and estimate how a viewer will rate a movie based on the match of these two vectors. The vector that contains the factors for the movie and the vector that contains the factors for the viewer. And now, one thing that we could hope is that maybe we don't have to specify these items a priori or by hand, but somehow that they will emerge automatically from data, and we could automate this entire process without having to go ahead and annotate things. So that could be maybe an interesting possibility. Here, this is the picture. It's an illustration from Abu Mustafa's course on learning from data. And this is the illustration for the Netflix movie challenge or movie rating examples, where again you have these sort of vectors with the components indicating some of those characteristics, and you try to match them by that match to a prediction. And this is a famous challenge that appeared, I guess now, well, more than a few years ago, but that was very influential. All right, so I should mention, of course, if we're talking about learning, we may try to catalog this type of learning in different ways and different categories. So a premise of learning is to use observations to uncover some underlying process. And there are three main paradigms: supervised learning, unsupervised learning, and reinforcement learning. I'm going to talk, to some extent about them, mainly focusing on supervised learning. Supervised learning, where we have some inputs and we're trying to say what category these inputs belong to. So we're trying to predict something based on an input. Maybe for unsupervised learning, we don't have a particular output in mind, or a particular label. But so an example could be clustering. So we just want to say which things are similar, but it's not. So you could maybe imagine that the cluster is kind of an output, so you could call that supervised. And reinforcement learning is maybe when there is some interaction between the data you're receiving and the desired outputs. But I'm going to be focusing on supervised learning, at least for today. Okay, so components of learning. Or components of supervised learning, maybe. So I want to think about another example. Here, the credit approval situation. And here, maybe we have given a data set. And the data set consists of a bunch of pairs, X and Y's. X is going to be a record for a customer. Maybe it tells us how old is the customer. Maybe it tells us the nationality, marriage status, study, salary, outstanding debt. Right, and maybe Y is going to be an output of interest, so some response variable of interest to us. Maybe in the case of this example, the credit approval setting, that could be whether this was a good customer for the bank. And all right, so you know, we have some predictors X and we have some response variable of interest Y, and we imagine somehow that there exists an ideal credit approval formula that will map any input X to the answer as to whether this would be a good customer or not. And so such a function f will map X to Y, that is yes or no. All right, so now what we want to do is try to figure out an algorithm that uses the data D to pick a function G that approximates this unknown ideal credit approval function. And so why would we care about doing something like that? Well, this ideal credit approval formula, maybe as I tried to explain with the example of the tree in the picture, is that we don't know what that function is. And so we don't have a good way to write that function down. And you know, if you were a bank and you have that function, you have jackpot, and you don't have to worry about anything else. So we don't know what that function is. So, but we can try to say, let's take this data set of examples, like the prior experience of the bank, and based on that, construct some other function G that is going to be an approximation of that, of the ideal credit approval function. And so once we have that, what we can do is use that to make recommendations on new customers. So a new customer comes to the door, and so the bank wants to know, is this going to be a good customer or not? And so they're going to just pass that data of this new customer to the function G. It's going to say yes or no, and then the bank will say, okay, so let's do business with this person or not. So far, so good?
Sure.
Thank you. Okay, components of learning. Maybe we have something like this, at least as I described it at the moment. We have here an unknown target function f that is going from x to y at the top. And from that function, somehow we're going to have generated some training examples, these pairs x and y. And I have indexed them from 1 to capital N, meaning there are n such examples. And then there's going to be this learning algorithm that is going to generate this hypothesis, the function g, that is somehow an approximation of f. And we're going to try and do that by augmenting this diagram with this hypothesis set that is going to be the universe of candidate solutions that we have, from which we want to pick this final hypothesis g. So we're not going to consider arbitrary functions, but maybe restrict attention to some special class of functions. But, so what is H? So what does this hypothesis say? And what is the learning algorithm? So, questions to ask?
So how important is this assumption that there is a function f out there, this ideal function? So without that, we cannot do it?
Yeah, it's a great point. We don't necessarily need to have a function. This could also be, for example, a probability distribution. You know, so a function is a deterministic mapping from x to y. And in reality, this could be a stochastic mapping. So it could be subject to length. It could be that two customers that have the same profile will not be both good. It could be one of them is a good customer, the other one is a bad customer. And that is not, of course, we don't want to exclude that. So this is a very simplified scenario. The other thing that I haven't illustrated here is that
for some reason it went for sleep.
we have this, if you assume that some solution exists, then you can at least approximate those areas.
I see what you mean. Yeah, yeah, I see what you mean. Of course, real life is complicated. So in reality, maybe even if there existed a function, maybe that function is not constant. It's going to be moving along.
Yeah.
So it's not going to be always the same function. It could be that customers who had a particular profile were good last year, and this year they are no longer good customers. So somehow it could be there's a temporal component that is not being modeled here. Also, I have not said anything about how this data X is being generated. I'm just saying the relationship between X and Y is described by some unknown function F. And I have just told you that such a function could also be stochastic. So it doesn't have to be a function as such, but it could be a conditional probability distribution. Right. It is conceivable that, that there are other variations that might be interesting in practice. Generally speaking, and I think this is true in a lot of cases, it makes sense to actually formulate a model, a formal model that is not perfectly accurate description of reality, but that allows us to do mathematics. And this is a setup in which we can do a very deep and very extensive mathematics, and it can be generalized in many interesting ways. That being said, some of those more general cases are still open. Like, if you start saying things like this function, I'm going to be allowed to interact with this function, or I'm going to be allowed to change the way that this input data is generated. All those are generalizations where there are still boundaries in what our current theory can give you. Other comments? Yes.
To avoid talking about the underlying target function, the other setup I've seen commonly is you just talk about a loss defined between any k as you sample the distribution.
I have not talked about that yet.
I wanted to the point when you saying you need to know the target function exists, and you can just talk about the infimum of the variable function as long as expectation.
Oh, okay. So you're saying just the way that we generate the final hypothesis?
Yeah, so you don't need to necessarily assume the target function exists.
Yeah, well, you're going to have a criterion to select the final hypothesis. And so the way I'm going to formulate that criterion is by trying to minimize a loss. Sure, you could maybe you could have a different reasoning in mind as to how you want to generate the final hypothesis that does not assume that there exists a target function. But the way that I have motivated the problem is that we want to be able to make predictions. When say somebody gives us a new customer, we want to be able to predict if that's going to be a good customer or not. And but maybe you have other. That's another really good point, and I'm glad you bring that up, because ultimately, the objective of whatever you're optimizing or learning is something that you as a developer are free to choose. And there is also not a canonical way of doing that. So if you have a particular objective, practical objective in mind, maybe there is a good criterion to the quality of the solution that you're creating. And that in itself is not obvious. But that quality criterion is very arbitrary. Right, so, but that comes to the question, well, I have not said that yet. So, but how do we come up with the final hypothesis, and what is the learning algorithm, and what is the hypothesis set? Okay, here is a simple example, and maybe the most simple example. Hypothesis set. Okay, first the hypothesis set H together with the learning algorithm are called a learning model, and here X, maybe we will call it the input space. This would be the features of the customers, and Y here the labels. That's the output space. +1 for good customer and -1 for bad customer. And maybe we take as a hypothesis space the space of all signs of linear functions. So this is an affine linear function on the input features of the customer. So this is a weighted sum of all those attributes that we have about the customer. So salary, outstanding debt, etc. Maybe we add an intersect to that, and then we take the sign. So maybe if the average or this weighted average is positive, we may say it's a good customer, and if not, not. So this is simple because it is linear. So it's basically saying, there's some kind of an ideal direction, like W potentially, that if the attributes of the customer are well aligned with that, then this is a really good customer. And everyone who is not aligned with that direction is a bad customer. But nobody says that this is the way that customers look like. Okay, this simple model is a linear classifier, or also known perceptron. And then for this learning model, what we could do is, so we can also write it a little bit more succinctly like this. So if we just absorb the intercept here into the vector W by appending a component 1 to the vector of x's, and then when we do the inner product of this, we obtain precisely the affine linear function that we have there. And we just basically take the inner product, take the sign, and this is our prediction. Then there is a particular algorithm that we can use that is going to use it's the perceptron learning algorithm that is going to take, for every misclassified example, is going to do a modification of the parameters to try to make them align with what the data was telling you. So the data was saying that maybe some particular data X was a good customer, but when you evaluate this function, this candidate function, it tells you the opposite. So they disagree. If they disagree, then you're going to modify the parameters to add something to the current value, which tries to make the output be consistent with what's present in the data. And so this algorithm, this perceptron learning algorithm, will repeat this procedure until the number of errors no longer decreases. So until, yeah, so, okay. Good idea or bad idea? So, well, as it turns out, this very simple algorithm actually will end up classifying all the training data correctly. So we'll end up finding weight vector of this parameter vector W that manages to represent a function that is consistent with that training data, provided that the training data is linearly separable. In other words, provided that such a solution actually exists. Okay, question for you. Okay, maybe first question, or two questions, I put it here. Can you obtain a short proof for this? So can you actually prove that this is true? Has anyone proven this before? Okay. Okay. Can you picture proving this at lunch during the afternoon? Okay, good idea to do that. Okay, now I should add up to the set of problems to obtain the short proof for this. Mine here, short proof, not a long proof, a short proof. Okay. That's the bottom line. It's not trivial, I think, and there are beautiful arguments as to why this is the case. But there is another interesting question here, and that is, so the statement here is that if there exists a solution, this algorithm will find it. So what happens if there does not exist a solution? So what is going to happen? So what is this algorithm going to do? So is the algorithm ever going to stop, actually? Because the algorithm is supposed to run until the errors no longer decrease. That's all. So, okay, so are they going to start increasing, or are they going to start doing what? So, okay, maybe the algorithm is going to stop whenever it goes up again, the error. But is it going to be able to converge to a particular value, or is it going to start accelerating? Guesses?
So here we have these two outputs +1 and -1, right?
Yes. So, right, our hypothesis is outputting the sign of this linear function. And so is going to be plus
It has to match.
plus or minus 1, right. So whenever it doesn't match with the y that is given in the data, we're going to modify that weight in this way. So the particular x that we have, let's say it didn't match with the y, so then we're going to, if it was positive, then we're going to be adding that x. If it was negative, we're going to do the opposite.
What does the error no longer decreases?
Right, so sorry, I should have been more explicit about that. The error is the number of misclassified training examples. So we are given this data set, it's a list of pairs, and our function h is going to be consistent with some of those pairs, but maybe not with all of them. And the number of pairs with which it is not consistent, that is the number of errors.
Okay.
So if no solution exists, is there a best possible approximate solution? And are there many of them? Maybe several. Okay, so it's nice, nice to think about. Okay, it's an illustration. Sometimes the way we draw this model, this perceptron, so if you call it a linear classifier, maybe you don't draw it like this, but if you call it a perceptron, maybe you draw it like this. So each of the nodes here is one of the components of this input vector x, and we are attaching these edges with some weights, so meaning we are weighting those values, and then we are adding them together here to create this output value y, and maybe we apply a sign after that. I have added here another node with a constant with a value 1. This is just to represent that intercept that is being added to this linear part. And so on the right part, what I plotted is just a situation where x is in R2, and maybe in R2 we have well, two coordinates. So every one of the points here, yellow and blue, are input data points, and I have colored them according to the label. So if the label y is -1, maybe blue, and if this +1, yellow. That's the training data sitting in part 2. And the red line is going to be the classification boundary of the perception. So basically, we have put here a normal vector, and everything that is pointing or has a positive inner product with that normal vector is going to be classified positively, and everything that does not have a positive inner product with it is going to be classified negatively. And this example, actually, I had a kind of an animation, but it's kind of not included here. But this is kind of showing the dynamics of this simple perception learning algorithm. And it converges, and you will find the solution. That clearly separates all the yellow points from the blue points. Okay, so then this is another example, a very simple example. This was, it's exactly the same thing, it's just that now, so maybe we're going to be thinking just that the data is it's a postal card, an address, and we read that out as a raster pixel image, and each of those pixel values correspond to numbers, like the intensities of colors. So we arrange them as a long vector, that's our input vector, and then we want to apply a perception to this and try to classify what was the digit. So this is a low-dimensional representation of what that could be. Maybe some of our data corresponds to handwritten digits that are 1 or handwritten digits that are 4s. And we can apply the simple perception algorithm to separate those two, 4s and 1s. And that actually works remarkably well. So you can actually classify digits 4 and 1 with a high accuracy with a linear model, with a simple perception. So you don't need a very complicated neural network to do that. As a matter of fact, this low-dimensional representation is just taking, for the X component, what I did was to plot the average pixel intensity. So take the image and take what is the average color, And for the y component, I plotted the square image antisymmetry. So like if I were to flip the image, left, right flip, how different it is from the original one. So that's something that you just compute it for a given image and just plot that as a coordinate here. And all those digits here, this is an example of a 1 that would fall in here in this two-dimensional plane. And with respect to those two features, a simple linear model classifies here those digits with
Whether it's here.
Yeah.
Maybe I'll move this thing.
Yeah, in a coffee break, I'm gonna disable that sleeping function.
okay, with not too bad an error. Well, here is not perfect. You can tell, I put here, this is making 6 errors for this data set that has maybe 50 data points. But yeah, it's remarkable. It's like 90% accurate. Yeah. But once I tell you basically that this low dimensional representation is saying something about symmetry and the average intensity of the pixels, that may be obvious because you can tell that a digit of a 1 has less bright pixels than a digit of a 4, which has a much longer stroke. So, those are very simple features that you could use in order to tell these two things apart. This is actually an interesting point because this is one thing that, people used to do in the past and are coming back to in the present, which is expert systems and basically handcrafted features or handcrafted solutions, or is trying to come up with writing down explicitly what this ideal function is. So if I could say, how do I tell a 4 and a 1 apart? I would say, well, one of them is symmetric. And so I would just come up with a way to measure how far from being symmetric the image is. And if it is far from being symmetric, I would just say that it is not a 1. So this is almost what is happening here. But maybe these are not the ideal criteria. It's just that they are more subtle and we just don't know how to put them in words. Yeah, nonetheless, these two features here will find out.
So is this red line is that ideal function?
Is it the ideal function?
No, it's not.
No, it's not. Well, I don't know. Why do you think it's not?
Well, I mean, the ideal function supposedly should correctly classify everything, right?
Should it?
I know it's not an exact answer, but you could possibly shift the red line, pivot it a little bit, and incorporate one more correctly identified 4.
Okay. Yeah, you could reduce the training error further. That's true. Okay, so an ideal function does not have to attain 100% accuracy. It does not have to classify it incorrectly because, this is the same topic that came up at the beginning. Do you always have a function? It could be that it's actually a stochastic behavior that you're trying to approximate with a deterministic function. In that case, the ideal function may be base classifier or something a classifier, which will still make mistakes. No matter how complicated you choose a deterministic function. So, this two-dimensional representation of the data, if you wanted to find a single deterministic function in this two-dimensional representation, it may be that there is not a single deterministic function that is always correct. Right. Nonetheless, I understand your point. Yes, so taking a linear model or a linear classifier, just a straight line, is very simplistic, and arguably, maybe there is going to be something smarter that one could do. Yeah. Also, this is only showing two features. Maybe if we were using the entire image, that would be much clearer. But think about it. So sometimes, humans cannot read a ledger, so you cannot tell a 4 and a 1 apart. And so if we cannot, so is there actually, at some point, that becomes a little bit subjective too. There is not really a correct answer. And so maybe that's indicative that, that even the ideal function might actually be making mistakes. don't know if I replied to your question. Or you probably-
Well, I'll think. No, yes.
Okay,
So you used the perceptron algorithm to get this linear classifier,
that's right.
and so then since it's not linearly separable, how did you like determine after some number of iterations you're going to stop?
I believe so, yeah. There is something called a pocket algorithm. So you're optimizing, and then maybe you allow yourself to optimize for a certain period of time, and then you're gonna go back to whatever was the intermediate solution that achieved the lowest value.
Okay.
So maybe I change my question. So if you have a data set where you have a line that separates bad credits with good credit, will that be the ideal function?
If I had a line that separates bad credit, this red line,
Yeah, if there's a red line that says if you are below the red line, you are bad credit, a bad customer. On the other side, good customer.
that would be our hypothesis for what that is. But I'm not suggesting that this is the ideal, beyond us. This is the best we could come up with. Yeah. So it's our hypothesis G for that ideal function. We may presume that the ideal function exists, but I'm not suggesting that this is the ideal function. It's just the approximation we came up with by running this perceptron algorithm. Yeah.
So kind of, excuse me, talking about these like handcrafted feature ideas. So obviously we would just hope that, like, let's say there are, in our data set, there are some features that are more important than others. We just hope our algorithm learns that. If we have a priori knowledge of some features, of the importance of some features, is there a way to like implement that into this sort of simplistic structure that we have to speed up the learning process?
Sure. Yeah, you can, for example, just take those features and discard everything else.
Right, I guess. Is that like in the case where it's not so, that you can make the decision just based on these? Like let's say you have, a confidence interval or like a probability distribution based on one of these features. So does that sort of question make sense in this context?
If you have a priori knowledge of what the good features are, you
Right.
definitely can use that. Yes. Because, so features are not necessarily kind of just components of the vector, the data vector that was handed to you. So features could be computed from the raw data features, and the computation could be quite convoluted and not obvious. And so if you have a way, if you already know what is the combination of properties that matters, you can definitely leverage that. So as a matter of fact, we use a lot of that in what is pre-trained models. So many times, for example, we will take a huge neural network that somebody has trained, and we will use that to process our own data to try and obtain those features because we believe that they are good ones, and with them we're gonna learn only using those new pre-processed features that we believe are good. So of course, once we do that, we don't have to actually, learn from scratch that computation, but it has done by somebody else for us. So that definitely can go a very, very long way. And I think in a lot of the applications today, people will try to leverage at least pre-trained models for other features. That being said, there is so in mathematics and in data science, so there is this subject, topological data analysis. I think it's very exciting because, it's kind of handcrafted feature, engineering, but there is a lot of debate also on how can one leverage them, or how can you tell which of those topological data analysis features are useful or relevant, or how can we actually combine them with an actual data-driven feature learning algorithm.
Right, and maybe this is a little too off topic, but like, does that sort of integration require a completely separate learning algorithm, like integrating a separate learning algorithm, or maybe that's not a learning algorithm, but like integrating. I guess it would depend on the case, but I'll clarify that.
Okay, yes, but keep that thought in mind and let's come back to that. Okay. So that brings me to this topic, learning versus design, one that I enjoy dearly and one that is kind of making an incredible comeback. So there was a time, there was a time when a lot of people said, okay, deep learning is brilliant because we no longer have to think about how to come up with some features. We're going to have a neural network, identify those features by itself, and we don't have to bother about it. We're going to have everything be learned from data in a black box fashion. And that is a big relief if you know, or maybe not. So if you spend maybe 10 years of your life working on good features, like there are specific features for natural images, there are kind of features in images that allow you to say something about them, or there are some other features for audio signals that you can compute, or this topological data analysis features that people can work very hard on formulating them and trying to prove properties of them. And then you still have to apply them and see what they do. And then, if somebody that says, no, I don't want to bother with that, I'm just going to do some black box thing, and it's just going to use the data as it is and do some high-level algorithm or optimization procedure, and then automatically it's going to select and identify the features that are relevant. And so there was a debate about the notion that if you already know what the good features are, it should be useful to you, much like the question that came up here. And but the issue is that how do you know that you have all of them? Like some of features are easy to identify, like the ones that I showed you for the ones and fours, like the symmetry, but maybe there are some other much more subtle features. Same is for images. You could say, whatever the features are, I know that they have to be invariant to rotation, so because that doesn't change the digit, or translation doesn't change the digit, but or shear, maybe shear like that, you stretch the digit in one way or the other. So you want to maybe come up with features that are independent of those modifications of the data, and because that should be indicative that you are not bothered to care about things that are just going to be confounders. So the issue is that how do you actually know if you have all of them? And there's kind of this dilemma of learning versus design. And the reason I said this is, however, again, very contemporary is because everybody's talking about geometric deep learning, everybody's talking about equivariance and invariant networks. And a lot of the things that are going on in there is to try to come up precisely with that. So how do we develop an architecture that responds precisely to certain types of expected properties of the data or of the problem? Like this invariance, maybe people tend to relate that to translation or associate that with convolutional networks. And now you have a generalization of a convolutional network that may be an illustration of trying to take into account all of those invariances or equivariances. All right, so learning versus design. So learning is based on data, and design is based on specifications. Specification, would be something that we say by hand. So maybe to classify the images or the handwritten digits, we could try to write a list of properties characterizing a line. It is symmetric, it is straight, vertical, and try to obtain this function analytically. So if verticality is higher than 0.3, then it is a 1, something like that. And both of them are very valid approaches. However, in many cases, specifying the classes is very difficult, or specifying what these properties should be is very difficult. And that makes this design approach unfeasible. The other one being that maybe we sometimes we don't know how many of these properties or features are necessary. Right, here, these are two examples of functions, right? Like one is the classification of digits, but you could have another example. Here is like a chess or Go, So you're giving us an input, a chessboard, and your output is kind of the optimal move. What should we do as a player? So instead of outputting a 4 or a 5, you should output here whatever the code is for the move of a player. So this is kind of very general. All right, so here's a couple of examples of problems that one might think about. So what approach, learning or design, would you consider more promising for the following problems? First, determine at the age at which a particular medical test should be performed. Ideas? Second, classify numbers into primes and non-primes. Third, determining the number of real roots of a polynomial. Fourth, detecting potential fraud in credit card charges. Next, determine the time it would take a falling object to hit the ground.
Learning would fit more.
Hmm?
I guess learning would fit more than design.
For determining the time it would take a falling object to hit the ground.
For the majority of them, I would say.
Okay, and last one, determining the laws governing planetary motion. Okay, so you want to produce a single answer for all the questions?
No, that's great. That's far from
That's great. Well, I mean, somehow I think it's a trick question in the sense that even if we decide to do this by design, what's going to happen is that we're going to be making observations of our reality, of the problem, and then after we have digested it, we're going to formulate a hypothesis and try to write it on paper, and that's going to be our design. So somehow we are also learning.
which is also part of learning, right?
Yeah,
Which is also part of it.
exactly. So if you consider our own acquisition of expertise as a learning part, for sure, the end-to-end computation, you could actually regard it as learning. But so I guess some of the interesting things here is that, and I'm gonna maybe say a few more words about that in just a second, but some of these problems you might think that actually they are very clearly and sharply specified mathematically. Like, for example, classify numbers into primes and non-primes. This is something that usually you would actually write down a definition for what is a prime number, and that is your classifier. Right. The issue might be that actually verifying that definition can be expensive. Similarly, determining the number of real roots of a polynomial. So maybe what we want to take as an input are the coefficients of the polynomial, and the output should be a number of real roots. And in some cases, this is known, and in many other cases, it is just not known. So the decision, that decision criterion, kind of discriminant criterion is maybe just not known. So it is known that maybe it exists. So maybe that's an example there where we know it exists, the ideal function, but maybe we just don't know what it is. But it's going to be so horrendously complicated, and we don't know what it is. All right. And for the laws of planetary motion, that's quite interesting because, at least in my view, this is one of those typical problems where the laws of planetary motion certainly are mathematically written as laws. But this is a problem of data science. Actually, it's a problem of observation and trying to come up with a hypothesis about those observations that is simple and that captures that behavior nicely. The question is, can you do it based on data and some kind of automated fashion? All right, so then just maybe to wrap up, so learning versus design. So learning appears to be most useful when a pattern exists, we cannot pin it down mathematically, and we have data. All right, so interestingly, many settings satisfy all of these items, including problems in mathematics, which is, I think, one of the most exciting things happening these days. Okay, I'm going to stop here.
So the question, if anybody has questions, feel free to ask. Drop the lecture, there are any questions. After we'll have 10 minutes break for the next